Hello mathematicians, welcome to our first part of our first topic in Extension 2 Maths, the complex number system. Now you're already aware that the number system of real numbers can be broken up into rational, those that we can express as a fraction, and irrational, those that we can't express exactly in any other way than their irrational form. Things like the square root of 3, for example. But we're going to work in this topic on complex numbers. And complex numbers are all hinged around the fact that we've got now a solution to the square root of minus 1. And we represent that as I. So I is the square root of minus 1, and then obviously I squared equals minus 1. So complex numbers end up being written with a real part and an imaginary part. So z equals x plus iy is the layout of a complex number. X is the real part, y is the imaginary part, and the I is equal to square root of minus 1. So what complex numbers allow us to do is to solve the problems that involve negative square roots that we would have simply said before are insoluble. So for example, we can write the square root of negative 25, or we can simplify that. And we do that using our properties of surds. So we can think of minus 25 as being 25 times minus 1. We can take the square root of 25, which is 5, and we can take the square root of minus 1, which is I. So the simplified version of root minus 25 is 5i. It's a complex number with no real part, but an imaginary part equal to 5i. Likewise, z equals the root of minus 7. We can think of that as the square root of 7 times the square root of minus 1, and the square root of minus 1 we can just write as I. So we can write the complex number in this form. We can also now solve quadratics that we may not have been able to solve before. So we would have previously, for example, come to this quadratic, check the discriminant, which was b squared, which is 16 minus 4ac, and we would have found we got a negative discriminant, and we would have said, well, no real roots. Now that's true, there are no real roots, but there are complex roots. So while this parabola doesn't cut the axis on the xy plane, we can nevertheless talk about values of x which make this equal to 0. So we can use our quadratic formula. So when we plug into our quadratic formula and we get a negative discriminant, that negative discriminant can then be simplified. So our discriminant is the square root of minus 36, which is of course root 36 times root minus 1, and root 36 is 6, so we would have 4 plus or minus 6i on 2, and then we divide through by our common factor of 2 to get 2 plus 3i. Likewise, we can do some different things with what we would have formerly thought of as difference of squares. So when we got to x squared minus 4, we know what to do. X minus 2 times x plus 2. X squared plus 4, well, we've hit the end of the road in extension 1, but in extension 2, we can rewrite that as x squared minus 4i squared. So I squared, of course, is minus 1, so minus 4 times minus 1 is plus 4, so all we've done is rewritten. However, in rewriting, we have created a difference of squares. So the square root of the x term is, of course, x. The square root of 4i squared is 2i. So we have x plus 2i, x minus 2i equals 0. So we have two solutions, plus or minus 2i. So, in summary, what have we found? We've found that we can have quadratics which, although they have no solutions over the real field, can be solved over the complex field. There's also one other thing to notice, that if a quadratic equation has real coefficients, in other words, if we look at our example here, the coefficients are 1, negative 4 and 13, which are all real, then if it has one complex root, the other root will be its complex conjugate. Now that's a term we haven't come across yet, but we've used conjugate before. So if one root is x plus iy, complex conjugate will be x minus iy. So they're the two roots. And as you can see up here, that's the case. 2 plus 3i and 2 minus 3i are the roots. Also notice that what we did with the difference of squares is a technique we have to become familiar with. So if we have a sum of squares, we can change it into a difference of squares using complex numbers. So that becomes a plus ib, a minus ib. Again, notice that those two are complex conjugates. So have a go now at number 1 in set 1.